Hello everyone, welcome to the GEOTOP-A seminar. Today we'll be listening a talk by Dmitry Kozlov titled Simplicial Models in Distributed Computing. So Dmitry, please.
Okay, well, thank you for inviting me to give this presentation. So the title is Simplicial Models in Distributed Computing, and I'm logging in from University of Bremen in Germany. So what I will talk about will be applications of what we call combinatorial algebraic topology in the theory of computing, more specifically in the theory of distributed computing. So let me start with a couple of slides just telling you what we mean by combinatorial algebraic topology. So if you want, if you cannot hear me well, just tell me, or if there are any questions in between. Okay, so combinatorial algebraic topology is concerned usually with computing invariance, same way as algebraic topology, but also it is also more concerned with simplicial structure itself, as we will see in our examples. And we are working with what we call combinatorial cell complexes. Today it will be just all simplicial complexes. And we also look at it by combinatorial means. So first, what we mean by combinatorial cell complexes. So classically in topology, you can specify cells and the attachment maps, and you can ask that it's locally combinatorial by just restricting yourself to very few maps which are allowed as attachment maps. So usually this will give you some simplicial complexes or polyhedral complexes or things like that, where you restrict yourself. So that the attachment maps can be given by combinatorial data, which is not usually the case for general continuous maps. But also here we have also combinatorial globally, which means that for each cell or for each simplex, we will have an index, which will be a combinatorial object. So in our applications today, we'll have different combinatorial objects, which will index different simplices, as they will come from the theory of computation. But in general, it can be also graphs, graph colorings, and so on. All kinds of things can index the cells or the simplices. And taking boundary in the simplicial set will have to correspond to some operation, some combinatorial rule of dealing with your indexing objects. So both of this, indexing the simplices with combinatorial objects and also specifying the boundary map using some sort of combinatorial rule gives you such a thing as combinatorial cell complex. And once you have this, you have, of course, the usual tools of algebraic topology to your disposal, but also, since you have underlying additional structure of combinatorial description, you have all sort of tools from the combinatorics. You can match things, order them, label them, and so on, whatever you want to achieve. So today, for example, when I get to the main open question, it is some sort of question about existence of a labeling of a certain simplicial complex. So just to close up this very short intro into combinatorial algebraic topology. So if you're interested, there is a book which is now 15 years, has been written 15 years ago on the subject, which contains nothing about the distributed computing because that came later, but which contains other applications. So for example, the graph colorings and things like that. Okay, so what I would like to do now is to proceed to distributed computing. So I understand that the audience doesn't deal with computation theory of computation every day, especially with distributed computing. So I planned to say a few words or actually give a little introduction from scratch into the subject. For distributed computing, you can think of it as a sub-subject of theoretical computer science, which concerns itself with performing computation in a network or in some model, whatever model you take. So it's not a usual computational model like Turing machines and so on, distributed model. So for now, I will now talk for a while just about distributed computing, what it is and what people are interested in. And then I will connect it to topology by introducing simplicial thinking into this context and giving simplicial models, and then formulating some open questions. And also results, but I'm, of course, as all mathematicians, mostly interested in open questions. So in this setting, in distributed computing, let's say we have n processes performing a certain task, and they communicate in some way. So as in all of these things, you have to make a choice. There are usually different choices to be made, and what's a bit confusing is that you will get a different model. So in a sense, you have many theories, depending on which choices you've made. So first choice you have to make will be what kind of model of communication do you use? So there is one of the first models of communication in distributed computing was the model which is called message passing, where you have a peer-to-peer network and your agents just send each other messages in this network. What we will look at will be the so-called read-write model, where instead of a network, they have a shared memory, and they read or write to this memory. And this is the way they communicate. And one other choice you can have, which is in distributed computing, called immediate snapshot, is that you read the entire memory at once. For the questions of solvability, it doesn't matter, and it turns out that also for questions of complexity, it's not that important. More complicated, there is models with read-write with other primitives. So these operations which you can perform are called primitives, and read and write are such primitives, but there could be more. So so my talk is completely theoretical, but the distributed computing and also the theoretical distributed computing is completely theoretical subject, but it has to do with originally, it grew from design of computer chips. And when you're designing a chip of the computer, you have to bake in certain operations already on the level of the chip. Which operations will it perform? And they're called primitives. And so one of the co-authors, I wrote a book about this, and one of the co-authors, Morris Herlihy, for example, spent a regular time at chip making companies so that he is informed about different challenges which they're facing. And in a sense, this whole subject of theoretical distributed computing came about out of necessity, because it turned out by designing of these chips that some standard tasks were not solvable, and one needed to develop theoretical framework to understand more about that. And of course, it's not very interesting to study modeling in the network, because such models can usually be replaced by non-network models. So you assume some sort of system, you allow some sort of failures. So we will allow crash failures, but there are also such things as Byzantine failures and other type of failures. So you just have to specify what do you allow in your model. So crash failure means that your agent, which is communicating, just stops communicating. But you don't know, did he stop or not? So since we also have a timing model, you don't know if he's very slow or he crashed completely. That's, of course, usually the difficulty which organizers are facing when they are waiting for a title and abstract from a speaker and he doesn't reply, and they have to make a decision if he has crashed or if he's just very slow. And that's kind of failures we have to cope with. But there are also other models, more complicated, where you ask for Byzantine failures. Byzantine failure means that as the agent send information, but it may be wrong, may be corrupted. So, theoretically speaking, it's also possible to design protocols which will solve your task anyway, even if the information is corrupted. And of course, there is a choice of timing model. Most interesting is so-called asynchronous model, which means that they send the messages, but we don't know in which order, and we have to deal with not one possible execution, but a variety of different executions given their algorithms, or what's called protocols of these processes. And we're interested in the possibility results and also in complexity results. So like I already said, so there are different models of communication, and there are many theorems in the subject linking them and proving equivalence, computational equivalence between different models. So for mathematical purposes, if we want to make simplicial, construct simplicial model, we pick one, which is called also standard model of communication, for which our simplicial models look nice, and we can proceed to work with them. So in the standard model, which we want to pick, the processes communicate via shared memory, and they use two operations. So one is called write, so it just writes its entire state to the register. So we're not concerned about memory restrictions here, so he just writes whatever he knows at this point. Each time he performs the operation write. And also so-called snapshot read, which means he reads the entire shared memory. So read is usually reserved for just reading one part of memory, maybe just one register. So if he just reads everything at once, it's called snapshot read. But for our models, it's the easier one, and it turns out that it's actually, even though it sounds like a very strong model, the others can be modeled with, connected to this. So we allow crash failures, as I already said. And the protocols which one studies in this are asynchronous and wait-free. So which means there is no upper bound on how long it takes to execute a step. In other words, if it's a message, it may arrive arbitrarily late. And so in this model, all executions are immediate snapshot. That means that it works like this. So it's a restricted one. So you have at each step, you have a group of processes, they activate, then they write their state, and then they read from the memory together. And so it goes, and then the execution is also layered. So it means that there are rounds, and in each round, everybody should be one time. Should be there one time. So it means that at each round you choose an ordered partition of the processes, and then they go according to this ordered partition. First one group, then the second group, and so on. And then in the next round, some other partition. So let me give you first example, become more concrete now. So here is one task. It's called assigning communication channels. So you have processes, they use shared memory, and the idea is that you have a certain number of communication channels, or let's say it's also maybe good to have another example. You have maybe an airport, and you have planes landing, and instead of communication channels, you have landing passes. So the planes are coming in certain order. You don't know it in advance. They come in real time, and you have to assign to them landing strips. And so some communication with the flight tower. Or with this model here, communication channels, you just have certain agents which come, maybe over internet, and they want to, you need to assign to them unique communication channels. So the way they communicate is they simply come and then they simply write their ID. So the number of IDs, the universe of IDs is very, very large. It could be like a total number of all possible IDs, maybe like 1 million, but you have a restriction on how many of them come at the same time. Okay, so let's say at most 2 of them come at the same time. And then there are questions. For example, one question in this model, how many communication channels do you need to assign so that you will have a protocol distributing it. So it turns out that you cannot do it if you have maximal 2 at the time. You cannot actually do it with 2 channels. You can prove this. So let me rather give you an example of how you do it with 3. So here is a protocol here, which actually works. So that is written in words. That's like a typical protocol on this subject. So if you have 2 processes and each one has the following protocol. He comes, he writes his ID into the shared memory, then reads it. If he doesn't see the other process, then he picks the first channel. If he sees the other process, then he compares his ID with the ID of the other process, and then picks C2 or C3, depending on if his ID is smaller or larger. That's all. So that would work because, in fact, it would work in one round because there are 3 executions possible if you have 2 guys and they execute each protocol once. So the 3 executions correspond to 3 possible ordered partitions of 2 elements. So one execution would be that first comes the process number 1 and then process number 2. Right. So then if that's the execution, Then the process number 1 comes, he doesn't see the other guy, he picks C1. Then comes process number 2, he actually sees the other guy, then he goes to step number 3 here, compares his ID, and then he picks C3. The other execution would be the other way around, first the second, then the first. Then the second one would pick C1, and the first one would pick C2, because he would go to step 3 and then compare and then pick C2. And another possibility is they come at the same time. In this case, they both proceed to step number 3, and then the first one picks C2 and the other one picks C3. So if you try to do it with 2, it will not work. So for example, so you can actually prove it doesn't work, but you can try. One intuitive thing to do it would be to say, okay, why do we even need this? We can replace line number 3 by saying, if the other process wrote its ID, okay, he is there, then just pick C2. He probably picked C1. But that will not work if they all come at the same time, because they both see each other. So both will proceed to step 3, and then they will both pick C2. The problem is when you see that the other guy wrote his ID, you don't know if he sees you. So if you wanted to communicate further, you would have to go to the second round and so on. And in fact, you can prove that it's impossible. This kind of proofs used to be written in this theoretical distributed computing in a very lengthy way. So it's actually surprising. So I went to a few of the conferences in distributed computing when I was first learning the subject. And I got surprised that they actually prove a lot of theorems in this. I didn't realize how many theorems they prove. And well, some of these proofs are not really proofs in mathematical sense, but some actually are. Or they can be made into a proof in mathematical sense. But usually this kind of impossibility results are written over pages with different cases and quite complicated proofs. So one of the things which going to Simplicial models has done in the beginning at least was not just to prove new things, but also to simplify the existing results by producing very compact combinatorial topological proofs of things like that. And so in fact, even in this case, I don't think it's actually known in general. So if you have like n processes, what is the minimal number of channels? I don't think that's known. I think they're bounds. I think that's what's called hard renaming problem in distributed computing. Exactly the number. But just to give you a taste of other tasks like that, there is so all of this. Okay, so there is a set of so-called standard tasks. Okay, and the reason why there is because in this distributed computing, they have different models of computation. So because, like I told you in the beginning, you can make different choices. You can allow this fail, or other fail, or this communication. You can make a lot of choices. And once you've picked your computational or communicational model, you want to somehow classify it or to know which tasks are solvable, which are not. And these standard tasks are used for that. So you can say, well, in this model, so the statements will be like, in this model, you can solve this kind of task. So one of the standard tasks is called binary consensus. The binary consensus task is formulated as follows. So you have each process. It starts with value 0 or 1. And then it does whatever you allow it to do. It has a protocol which uses this communication system. And you're asking that eventually it will give an output, 0 or 1. And what you ask is that two things. One is that they all agree on the value. So either they all choose 0 or they all choose 1. And the second is that if somebody has, so if they decide on the value, this value has to be present with one of the processes. Yeah. Well, it's actually a necessary condition because otherwise you would have a very simple protocol. You don't even look at what value you has or what everybody else is saying. You simply say 0 and then you agreed. So you don't want that. So it turned out actually, that's actually one of the starting points of this whole subject was that people realized, this is a very standard task, binary consensus, and people realized that binary consensus was not solvable in the standard model, which made people think about being more careful about designing things. And then The next step is so-called K-set agreement, where each process has an input value from a bigger set. But at most K different values appear as output values of the processes. So the binary consensus would be 2 set. And then they have to agree on, so binary consensus would be 1 set. So they have some values, and then they have to agree on at most K different values. So at most 1, at most 2, and so on. And of course, only the values which appear as inputs are allowed. So even this is not solvable. So in other words, if you have 100 processes and they start with 100 different values and they have to agree, they have to eliminate one value. So they have to have an output, but it should lie in a set of 99. So even that will be impossible in the standard model. And then there is a task which is called weak symmetry breaking task, where you have processes with no inputs, just their IDs. And they need to pick outputs from 0 and 1 such that not all processes pick the same output. So in other words, they have to distribute themselves into 2 groups. It's called symmetry breaking because it's not solvable due to some symmetries, often. So all they allowed is to compare their IDs with each other. So I will look at this weak symmetry breaking actually as my main example. And if you look at solvability, for example, as I already mentioned, binary consensus and K-set agreement, they are both not solvable in the standard model. And the people who proved it got actually some prize. I forget the name they have in computer science. It was quite a big deal actually when they proved it using topological methods. By weak symmetry breaking has interesting answer. So it says that the task is solvable if and only if the number of processes is not a power of a prime number. So the smallest number of processes for which the weak symmetry breaking is solvable is 6, and then 10, and so on. But that's a theoretical result. So actually, as far as I know, there is no specific protocol which actually solves it. It's just proved that it's solvable. I don't even think that for 6 one has a protocol. I mean, I have a protocol, but it's it's like thousands of lines. Yes, maybe even more, hundreds of thousands, maybe. I don't know. Anyhow, so that was the end of my little introduction, just distributed computing. Now I want to connect it to the Simplicial setting. So how do we introduce Simplicial things into this? So let us see. So the first Simplicial complex which appears is so-called input complex. So in that, you can say that you have a number of processes and they have a number of possible input values. And then you simply say, okay, these are vertices of my Simplicial complex. So each vertex is labeled by process ID and a possible input value. And then you glue in simplices by saying which combinations of input values are allowed. Okay, so maybe all are allowed, I don't know. So, but that gives you a Simplicial complex. It's called input complex. Right, so just as a quick kind of brain teaser, if you start with n processes and they all have possible values 0, 1, and you allow any combination, then actually this input complex will be a triangulation of a sphere, because it will be, you have 2 vertices for each process, and then so it will be just a join of 0-dimensional spheres n times. You'll have a sphere. The other Simplicial complex you have is this complex of final configurations, which is very similar to the input complex. So it's again, the vertices are indexed by process ID and the possible output value. And you glue in a simplex if this combination is allowed as an output. So again, in the binary consensus, that would be just 2 simplices, 2 top-dimensional simplices, one with all values 0 and one with all values 1. And now comes the interesting part. So it's a Simplicial complex of all executions, so-called protocol complex. So like I already said in the beginning, unlike usual algorithms, when you have in distributed computing a set of processes which are executing protocols, there are many different executions possible. So even in our example with two processes trying to choose communication channels, if they executed the protocols only once, still you have three possibilities. So the number of possibilities, if you in this model will be, if you just one round, it will be a number of ordered partitions. Otherwise, it will be higher. So it's a very large number. It grows very, very fast. And what the idea here is that you create a simplicial complex which contains all possible executions. So the vertices in this simplicial complex will be indexed by process ID, so it's a process, and a possible view of what he sees happens in the execution. And then you will have top-dimensional simplices will be all combinations of processes and their views which are feasible under some execution among all possible executions. So that's called protocol complex. So that subject is actually now has been also strongly connected to logic. There are even conferences about it. You have basically the idea is that you have a number of vertices, a number of possible world views of actors. You have some actors and they have a view of the world, and then you put them as a simplex if there is actually a world where these actors have simultaneously this view. So none of them contradicts to each other. So there's actually realization of such a observation, which they do. So that's a more general thought. Here we are more specific with these protocols, but you can of course do it more generally. Okay, so these are simplicial complexes which you can associate with it. Input and output complexes are usually quite simple. Protocol complexes are interesting, but for the standard model, they will be actually, they have a complete combinatorial description because there will be certain simplicial subdivisions of a simplex, simply. Some subdivision which we call standard chromatic subdivision. It's a different, call it something else. But it also appears in different contexts also as elsewhere. Fine. Then for each, so in this slide on the right here, we have things like task specification map, execution. So all of these things is a terminology from computer science. And what we want is to translate it into in computer science, when they will be describing to you a standard task, they'll say this is a set of inputs, this is a set of outputs. And if we want to describe the task, we will tell you a task specification. So task specification will be, well, the actual description of the tasks. They'll say, for this inputs, we allow this output. For this input, we allow this output. So if you want to phrase it here, you will have to have a map which will take a simplex in the input complex, so some input configuration, and it will give you, well, not one output because it's distributed here, but a set of all allowed outputs for this input. Right, so that's a subcomplex. So therefore it's not a simplicial map, but what we call a carrier map. So a carrier map between two simplicial complexes will take a simplex to a subcomplex inclusion of the simplicity. We call this a carrier map. So there is one, even before you even started to do anything, just to specify the task, called task specification map. Then if you try to solve it, then there will be a protocol complex and there will be another carrier map from the input complex to the protocol complex, which is called execution map. So this map will take each input and map it to the complex of all possible executions given that input. That's called execution map. And then finally, when you're done, you also want to have what's called a decision map. So that map takes, if you have so what does a decision look like? A decision is like this. I am process name so and so. I have seen this and that, and I decide my output is this. So that's actually a simplicial map from the protocol complex to the output complex called decision map. And there must be some condition which connects all these things, which would be a simplicial rephrasing of the phrase, this protocol solves this task. All right, so we want to be able to say that in some strange simplicial way. So just to give it more specific, so I already actually said this, but let me have this slide again anyway. So the binary consensus, in that case, the input complex will be all vertices labeled, a number 0 to n. So that is 0, starts with 0, 0 to n, and one additional value, 0, 1. And this will be all possible simplices, right? So that's a join that will be a sphere. And the output complex, like we already said, it's two disjoint simplices, one all zeros and one all ones. And the carrier map delta, the task specification map, that's what it says. So if all of them are zeros, then it must be this 0. If all of them are 1, then it must be all 1. But if not, it could be anything. So it's a union of them. So that would be a rephrasing, simplicial rephrasing of the binary consensus. So for the protocol complexes of these things, we have the following interpretation. So these are, as I already mentioned, subdivisions of simplices. So the protocol complexes for one round of this, well, all of these words just specify this model, the standard model. I could also have written simply one round standard model. N+1 processes, that's a certain subdivision. You can prove that it's collapsible and so on, of a simplex. So, we're all familiar, so I can describe to you formally, but I think it's better just to say it an intuitive level and you can easily fill in details. We're all familiar with the bodycentric subdivision, of course, of any simplicial complex, but of a simplex, for example. And now, instead of having one barycenter, I move each barycenter of each boundary simplex a little bit in all possible directions. So, in other words, here on the edge, for example, I would usually have a barycenter here, but it's on 2 dimensions, so I move it a little bit to that one and a little bit to this one. So I have, and here I move it a little bit away. So you move it a little bit away from this one. We have 3. So there are different ways to phrase this. You can phrase it as join or different things and so on. But that's the idea. So each time you put in a barycenter, you actually put in a simplex by moving the barycenter a little bit from each of the vertices which generate it, right? Each barycenter is a linear combination of vertices, so you just push it a little bit away. And then you will get a simplicial structure. So that's that structure has the advantage over the barycentric subdivision that it's chromatic in the sense that if you have a coloring of the initial simplicial complex, you will be able to color this one also with the same number of colors. That's of course not true for the bodycentric subdivision, because if I have a triangle and I colors. So whenever I say coloring, it always has to be different. For if you have an edge, then the colors should be different. Anyway, so of course, if I have a triangle, I have colors, for example, 0, 1, 2. And if I put in a barycenter, barycenter is connected to all 3 of them. So I'll need an additional color. So using barycentric subdivision will quickly grow a number of colors. Here, it will not. It will be the same. That mathematically, you can prove it for computer scientists. It's obvious because these colors are just names of processes. And so since this is a complex where if 2 vertices are connected, then of course it's different processes, and of course they will have different colors. Anyhow, so for example, here for just one iterated subdivision, you will have vertices. Each vertex will be labeled by a number, 0 to 2, and a set, which contains this number. And then you will have, there is a certain rule, combinatorial rule, which you can describe. But anyway, so I guess one way to think about this, if you look at on the left here, that is actually encoding. So if you look at the vertices, this is actually encoding all possible views of one round execution of the processes. Because if your process number is 0 and you just look, you either just see yourself, you always see yourself, of course, or you see both. And the same for 1, he either sees himself or he sees both. and the edges correspond to possible combinations. So a combination where 0 sees only himself and 1 sees both is possible, right? Because 0 maybe is first one and 1 is the second. And so is a combination where both of them see both, because maybe they came at the same time. The 3 edges correspond to the 3 cases which I was talking about before. But you do not have all, so of course you cannot connect 2 with the same, so you cannot connect 1 with 1 because it's the same process. But you also cannot connect this 0 with this 1, for example, because it's impossible to have an execution where 0 sees only himself and 1 sees on also. There is no such sequence. One of them will it's impossible. Okay, so I want to do 2 things. One, I want to formalize, push this through all the way so that I can formalize this whole language of standard tasks and the protocols which solve them purely in a simplicial language, so that if one wishes, theoretically, one can simply forget that it comes from the distributed computing, and then we just have questions about some maps between simplicial complexes and so on, with some labels. And then I also want to talk about weak symmetry breaking. And these are the 2 things I want to do. So you formalize it. You can formalize, first, you need to formalize the notion of a task itself. So it will be basically what I said before. You have, 2 complexes in the map, but then you have to be careful. Once you formalize it, you have to state conditions exactly what you are doing. So you have you don't have just a simplicial complex. You have what we call chromatic simplicial complex, because you also have a coloring, which are the names of the processes. So you have a coloring, which I like to phrase always as a map into a simplex, but you can phrase it in different ways. I think in combinatorics you simply just label and that's it, and you say this is a coloring. It's called rigid chromatic if it's pure. And the coloring is n+1 coloring. So in other words, so the pure complex means all the top dimensional simplices have the same dimension, and the number of colors is exactly optimal. Not always possible, of course. Now, if we have, but here it will be like that. So in input complexes, they will all be rigid chromatic. Now, if you have such 2 guys, then the carrier map is called chromatic if for every simplex, the simplicial complex to which it maps is also pure of the same dimension as the simplex, and it uses the same set of colors. These are all requirements which are quite strong from the point of view of simplicial model, but which are natural in computation, because you're taking a simplex which corresponds to a certain set, for example, of inputs, and you're mapping it to the set of all executions. Of course, it should be the same processes we are talking about here. So with this terminology, a task will be a triple of 2 rigid chromatic complexes. One's called input complex, colored by the set 0 to n and labeled by some set. We always ask that vertices are uniquely defined by the color together with its label, so they're not doublings. Same for output complex, just maybe a different universe for outputs, it's allowed. And then a chromatic carrier map. So anything like that, we want to call it task. So all of the standard tasks coming from distributed computing will simply give a mathematical object like that, 2 complexes and a carrier map with colors. And if you're interested in applying results back to the distributed computing, then you want maybe to look at the specific ones, but in general, you can of course study this whole things just without referring back. So for the protocol itself, so protocol, sometimes it's confusing. So that's what's called algorithm in consequential computing, but here the usual terminology is protocol, like internet protocol. A protocol for n+1 processes will be also a triple of 2 rigid chromatic simplicial complexes, the input complex and the complex of all executions, so-called protocol complex. Has a different universe from which it draws labels, which is called, we can call it views. And then it has an intersection preserving carrier map. So it takes each What it does is it takes each input configuration to the subcomplex of all possible executions given that configuration. And then you have this intersection property, intersection preserving property. And given this theoretical framework, you can now trace also purely simplicially what it means that you have designed a protocol which solves a certain task in distributed computing. So what it does is it's a certain relation, certain commuting relation. So very roughly said, it's so that if you take the input and then you execute, you land inside the allowed outputs. That's what it says here. So given a task and the protocol, we say that the protocol solves these tasks if there exists a chromatic simplicial map, delta, which is called a decision map. So that if I take some simplex sigma, take the subcomplex of all possible executions and apply the decision map, I will land inside the subcomplex of allowed outputs. Delta, remember, is the task specification map. So that's exactly praising that my protocol produces an allowed output given that input. So that's just commutativity. In a certain sense, commutativity relationship. So, if you want more specific, being more specific, that's how it works for the protocol which we were talking about. So remember the protocol which we had said you execute one. So for two agents which want to get a channel assigned, so you have three possible channels and you have two which arrived, and the protocol said, I look, if I don't see the other guy, I pick the first channel. If I see the other guy, then I compare myself to him and I pick the second or the third channel, depending. Okay, so in that situation, simplically, that would withdraw. So simplically, it would mean we start with a simple, one corresponds to the first guy and two to the second guy. Then you have the execution map, that should be a carrier map, and this is up above, this three intervals, this is a protocol complex. So for example, here is a vertex. This vertex here on the left, it corresponds to the first process and he only sees himself. This vertex corresponds to the second process, he sees both, then one sees both, and two sees both. And these edges correspond to executions. So here, for example, the execution, which is usually in the things they encode it as strings, write, read strings. So W1, R1, W2, R2 means write 1, read 1, write 2, read 2. So it means that the first came first, and then he wrote and he read, and then the second came. In the middle, you have a string W1, W2, R1, R2. It means that they both came together, they wrote, and then they read. It doesn't matter in which order. And they connect possible views. So for example, if they had the execution like this, W1, W2, R1, R2, then that's what they would see. 2 would see both, and 1 would see both. Okay. And now this arrow things on top, that's the values of the decision map. So on the right here, that's the output complex. That's the input complex, that's the output complex. In the output complex, you have vertices. You have 3 vertices for the first process because there are 3 different channels which you can assign. So there is a vertex called one is assigned C1, one is assigned C2, one is assigned C3, and 3 for the second one. And the edges are connecting all allowed configurations of outputs. So there are 6 configurations of outputs which are allowed. So if 1 is assigned to C1, then either 2 is assigned to C2 or 2 is assigned to C3. And so on, right? So you cannot have edges just on the left because this would connect assignments of the same process, and we only want to assign one thing to each process. And we also don't have an edge between here and here because we want to assign different ones, right? And here. Okay. And then a little bit thicker, I have drawn the simplicial map. So that's a decision map. And then you have a task specification map, and when, as we talked before, it will so we can say that it solves it if the whole thing somehow commutes. Yeah, so if you go up and then down, then you land inside the task specification. Okay, so that's a formal framework. It can be useful to keep some of the terminology, but the purpose of the whole exercise is, of course, to eliminate actually anything which is not anything which is not simplicial. So just to mention, so I have a book. So one of the persons is actually in Mexico, is Sergio Reisbaum, and the other, more thoroughly, he's in Brown University in the United States, and they're both actually in computer science, but which deals with this kind of questions. So it's also already 9 years ago, yeah, surprisingly long ago. Anyhow, and so summary for this part, it's not yet the summary of the talk, but I have a few more things I want to say. But just a summary of this part. So simplicial methods are useful in theoretical distributed computing, and I hope also that I show you that also the other way around, that we can get to interesting questions from the distributed computing, which are formulated purely simplicially. And so recent work provides rigorous foundation for this interdisciplinary area. This is actually one of the purposes of this book is to provide. Well, one has to be careful. So I can use the words rigorous foundation. So in fact, the people in computer science think it's already rigorous. But from a mathematician point of view, maybe a little bit more. Anyhow, and these protocol complexes are, in a sense, analog of configuration spaces. So in configuration spaces, in topology, we have maybe topological space including all possible configurations of something. And here we encode all possible executions of protocols. And the combinatorial topology of this protocol complexes is actually sophisticated and contains answers to distributed computing questions, depends on the communication model. So in this, very easy just taking the subdivision, but there are other models where you don't actually even know what spaces you get. You just have description, combinatorial description, but they're quite complicated. And the study of combinatorial topology of protocol complexes will also lead to new and interesting mathematics. So I see that I have 10 more minutes, and what I would want to do is to explain a question which is purely mathematical, purely simplicial, which would be interesting to answer, which is contained in this weak symmetry printing. So it has to do with this standard chromatic subdivision. So again, so the standard chromatic subdivision, like I say, you can define it by just combinatorial way, which means I simply give you in combinatorial language description of all simplices in it, and that's the end. Or you can kind of geometrically think about what I said, when you take the barycenters and split them like little particles away from the things which generate them, is a way. And there are also kind of different iterated ways to see this. So that's what I think it's not very difficult to write down the definition once you kind of get what you want to do, how you want to do that. So they're iterative. So they're defined in all dimensions of the simplex, and each next one on the boundary it will be the same. So this is for the triangle. If I want to define it for the tetrahedra, it will look like this on each of the boundary. Triangles, and then inside you'll have to hang in a tetrahedron upside down and then connect it to the boundary. So, and yeah. Okay. Yeah. So maybe right. So they're different. I don't know. So there's different objects which are connected to this thing. So for example, there is an object called flip graph, which is that you take a vertex in each of the triangles and then you're allowed to go over the edge, and that's called a flip. And actually, maybe that's just like a window into what it looks like. So then you will have a graph, and this will be all kind of labels of the vertices. In this case, the labels are, all possible ordered partitions of the set 1, 2, 3, and then because this has triangles, right? There are 13 of them. I think it's called Bell number or something like that. It grows very, very fast. And then if you connect to the two triangles, you have some operation on them. So for example, this is connected to the very beginning when I was talking about you have labels and then you have operations. So here the operation would be like, if I start here 1, 2, 3, and I go along label 2, it means I split 2 off the block here. Or if I go this way, I join it back to the right. And you can phrase it all in combinatorial language, and then you can move around using that kind of terminology on this thing. So the standard chromatic subdivision has the following properties, which are very useful, which makes it quite general. So, as I mentioned just before, it is if I do it for a simplex, then on the boundary of the simplex, it's actually the same construction, one dimension lower. Yes, so just like the standard subdivision would be. So that means it can be applied to any simplicial complexes, not just to a simplex. Right? You can just you can talk about standard chromatic subdivisions of simplicial complexes, and you can and also it means you can iterate it. So once you did it once, you can repeat it, and so that's actually the main thing to look at. So the iterated standard chromatic subdivision of a simplex actually is what needs to be understood in a certain sense. I'll tell you in which sense to understand things about weak symmetry breaking. So there is a certain symmetry here. So so for all subsets, if you have two equicardinal subsets, I and J, then we have a linear isomorphism between these two boundary simplices, preserving their order. And it's actually an isomorphism of the division as well. So I think the correct way to think about this, if you like, this language, is to think in terms of semi-simplicial sets, or sometimes also called delta complexes, where you have instead of simplices, you just have sets of simplices, and then you have a boundary maps according to certain rules. But it's not a simplicial set; it's not completely degenerate. You don't allow certain degeneracies. But semi-simplicial set. And in fact, for the weak symmetry breaking, the most comfortable, if you like this language, is to think about there is only one actually semi-simplicial set where you have exactly one simplex in each dimension. So it's not a simplicial complex anymore. So, or you can think about taking a complex, taking a simplex, and then gluing together, identifying all boundary simplices of the same dimension into only one boundary simplex by preserving the order, of course, of the vertices that you can do. I think you may actually get a dance hat if you do it for triangle, but you can do it for higher. And then you want to look at the standard chromatic subdivisions of those actually, as it turns out. So let me skip this. So that's actually what I was just saying. So if you have a labeling, so now we are looking at this object here. You take a simplex, and then you take iterated chromatic subdivision, standard chromatic subdivision of that simplex. And then you want to look at labeling of the vertices. And then you say that it's, the ones you compliant, if it's invariant under this isomorphisms I was talking about. So that's one way to think about it. So for a triangle, it would mean that it assigns the same value to the vertices of the triangle, and also on each edge there are identifications like you would have in the dance hat, and then it should be the same according to this identification. So one other way to think about it is that you're not labeling the simplex, the chromatic subdivision of the simplex, but you're labeling actually, you're taking this semi-simplicial set and you're labeling that. Then you can just skip all the conditions. And the main goal is that you want to find a binary compliant labeling, so to 0, 1, so that no n simplex is monochromatic. So it doesn't have all values 0 and all 1. So in fact, it's funny, but that reformulation is actually the same as the weak symmetry breaking in distributed computing. It's actually identical to this. And each time you can do that, if you can do that, then it will translate back to the theory of computation by saying that you can solve weak symmetry breaking for, here actually n+1 processes in T rounds of the executions. So there are theorems in this. So there is a Herlich-Shavit theorem, which says that if the number of vertices in the original simplex is a prime power, then there does not exist such a labeling. So the proof of it, I would derail too much this talk, but so in other words, well, they prove it a little bit different. They prove the statement that says they cannot solve weak symmetry breaking if the number of processes is a prime power, but formulated in our language, that's what it says, that there doesn't exist a labeling satisfying these conditions. In the other direction, there is a theorem of Castaneda and Reisbaum, which says that if it's not prime power, then actually there exists, for some t, there actually exists such labeling. So that's a solvability question. So in other words, that's what I was mentioning. So for weak symmetry breaking, curiously, you have it can be solved if and only if the number of processes is not a prime power. So the question which remains is what is the minimal t, right? So minimizing the number of iterations, it's easy to see that. Well, actually, you can prove it mathematically, but for computer scientists, again, this statement is actually trivial. So if you have such a labeling of the t-iterated subdivisions, then you also can extend it to the labeling of the t+1 iterated labeling. So for computer scientists, the statement translates into if you can solve it using t rounds, then you can also solve it using t+1 rounds, which is a trivial statement because you simply you can actually do it mathematically, it's not just extend the labeling. Anyway, and so the main question is what is the minimal value of t then? Because once you do it, how many complexity? So it's a standard question of complexity. So it's actually quite a hard question. So people try to work on this, and so the results before the simplicial methods were that that's double exponential. Even for 6, it's like at most 17, which is a very large number. It turned out, I proved some years ago, actually, not quite some years ago, I see. Anyway, that the following result. So actually, it's a strange result because it has to do with some number theoretical properties of the value of the number n, but that's what it says. So if you have a binomial identity, if you have a number n and you have a binomial identity of this type, right? So you have sum of binomial coefficients equal to sum of other binomial coefficients. You require they're ordered here. So 0 is A1. So anyway, so you require that 0 here and 1 here. And okay, so you have some other, so A1 should be at least 2, at least 3 actually, and B1 should be at least 2. And they are different, but if they're not different, you can just cancel them. It doesn't actually matter this condition. Anyway, so here's, for example, such identity. 6 choose 0 plus 6 choose 3 is equal to 6 choose 1 plus 6 choose 4. Okay, so if you have such an identity, then you can actually solve the weak symmetry breaking in at most 3 rounds. Or in other words, you will find a labeling, which is actually quite hard, but you can find a labeling satisfying the conditions we're talking about. So such identity will not exist if n is a prime power, which it shouldn't, because if n is a prime power, it's not solvable at all. If n is a prime power, then this left side will be 1 modulo this p, and the right-hand side will be divisible by p. So it will not work. But if it's not a prime power, sometimes it exists and sometimes it doesn't. We actually don't know when it exists and when it doesn't. But there are infinitely many values for which it exists. So for example, if n is divisible by 6, then such identity will always exist. But there are also infinitely many others. But also there are infinitely many values for which it doesn't exist. Anyhow, so that's kind of a mystery, which I think I will finish with. So, yeah. But it's kind of an interesting situation. So, just maybe to say it a little bit like this. So usually the questions of complexity in a classical situation, you have a complexity when you solve some you need to, I don't know, sort things, or I don't know, merge lists, or any computational task. People, it grows when n grows. Okay, and then in the complexity theories, they just want to know, does it work? Does it grow exponentially? Does it grow polynomially? Things like that. But here it's not so clear what happens. So if there are some number theoretical properties are satisfied for n, then there are some very fast solutions apparently, even though it's very hard to construct them. In fact, I don't think anybody constructed them. And it more depends, so there are infinitely many value strengths for which it's solvable in only 3 rounds. And then we don't even know if it, there is upper bound, if it's solvable in constant number of rounds for any n, this we don't know. So I skip the ideas of the proof. I just say that it's unclear at the moment for which n such binomial identity exists. We certainly don't know if 3 is a sharp bound and for which, and what's the bound for other n. This is all completely open. And we can summarize this by saying that the study of solvability of weak symmetry breaking task leads to a rich theory of subdivisions of the simplicial path. This was the initial work of Sergei Reisbaum and his student. But much structure remains mysterious. But simplicial methods can be used to design fast protocols solving weak symmetry breaking, but the explicit protocols in general remain out of reach for now. Okay, well, I'm sorry I had to speed up a little bit, but I wanted to get to this point. So I thank you for your attention.
All right. Thank you very much, Dmitry, for a very nice presentation. Do we have any question, perhaps?
Well, if there's no question, I can say something more, maybe.
Maybe I have just one question.
Okay.
Do algebraic invariants like homology appear as any sort of abstractions in this setting?
That's a good question. And in fact, that was my initial hope when entering this area, because before that, I was looking at graph colorings and using, in that case, it was Stiefel-Whitney characteristic classes in cohomology, which it turned out could be used as abstractions to existence of graph colorings. And I hope to have something similar here. But until now, not quite, no. The point is, it seems it's harder, it's more subtle. So unlike the usual topology, subdivisions are you have to be very careful about subdivisions here. Usually you don't have to be careful about subdivisions. But here you do, because the actual simplicial structure of these complexes actually has to do with the questions you are looking at. So I guess the short answer to this, it would be interesting to have it. And I think if one succeeded to connect to something like that, it could bring really a number of new insights. But for now, we've been bogged down at the more basic level of just the complexes themselves. Yeah.
All right. Thank you.
So maybe I just say one more sentence. So there is actually philosophical discussion about the last point here, where I talk about explicit protocols. And in fact, so there is a complete equivalence. There is a complete mathematical equivalence between producing such protocols, so in other words, algorithms to solve this task, and labelings on the subdivision of the simplex. However, if you have a protocol or an algorithm, it's in the eye of the beholder, because a computer scientist thinks of algorithm as something which says, I do this, I compare, like what we had, I take this, I compare it, I look at this, I look at it, and I decide, okay? But here, the algorithm, the protocol will be like, for each simplex, it will simply give you the answer. So the number of lines in the code of this protocol could be on par with the number of executions, which is very large. And then there could be other questions like you start to request that so for each n, of course, the protocol will be finite, but the lengths of the protocol may grow with n, which is, some people will say, okay, that's, But like I say, even for 6, I don't think there is an explicit protocol. Because it's very large. Anyhow, so there is also beef there about what exactly is meant by the existing protocol. But for mathematician, I think there is no question what means to exist.
All right, thank you. Is there any other question, perhaps? Well, if not, then I would like to thank Dmitry again.